Welcome to this explainer. If you're a focused learner trying to crack standardized test math, whether that's the GRE, the GMAT, or you're just looking to sharpen your quantitative reasoning, you're in exactly the right place. Today, we're going to fundamentally change our cognitive approach to solving complex math problems. We aren't just memorizing formulas here. We're looking at exactly how we think under pressure, drawing directly from some really fascinating source material on strategic test taking. So buckle up, because we're about to completely rewire how you tackle these exams.
Now check out this core philosophy from our source material. Speed without clarity is just a waste of time. You know, when that clock is ticking on a standardized test, your very first instinct is usually to rush, right? To just start calculating something, anything. But this quote stops that urge dead in its tracks. It establishes our entire theme for today, strategic planning. I mean, if you're running at top speed in the entirely wrong direction, you're literally just getting further away from the right answer. We absolutely have to know exactly where we're going before we hit the gas pedal.
Here's our roadmap for today's explainer. We'll start with clarity before speed, then look at algebraic systems, move on to ratio constraints and strategic percentages, and wrap it all up with some key strategies.
All right, Section 1, Clarity Before Speed, Activating Mental Engines.
So our source introduces this really brilliant metaphor. I want you to think of your brain as a complex machine with all these different mental calculation engines. But to turn those engines on, we need what the source calls apodictic knowledge. Now I know that sounds like a super heavy philosophical term, but it really just means clear, established, unquestionable knowledge that you can 100% trust. It's your rock-solid foundation. When you look at a math problem, you need to find this absolute truth in the setup first. Once you have that trusty foundation, then you can safely shift gears and apply speed without getting completely lost in the weeds.
Moving right along to Section 2, Algebraic Systems, and specifically, the green marble problem.
Okay, imagine the fast-paced stress of reading this on an exam. If x plus y equals 80, y plus z equals 120, and x plus z equals 160, what is z? Usually, our panic instinct here is to immediately start isolating variables, right? We think, okay, x equals 80 minus y, let me plug that into the third equation, but hold on. Let's take a purposeful pause right here. Our source explicitly warns us against going this long route. We shouldn't just start isolating variables one by one. Instead, we need to step back and look at the entire system to find that moment of clarity.
And it brilliantly illustrates how stepping back gets us straight to the answer. Instead of isolating variables, what if we just sum all the equations vertically? We get 2x plus 2y plus 2z equals 360. Next, we simply divide everything by 2, which leaves us with a beautifully simple x plus y plus z equals 180. Now here comes the magic and the final step. We already know from the original problem that x plus y is 80. So we just substitute that right in. 80 plus z equals 180. Instantly, we see that z equals 100. No messy substitutions, no solving for x or y first, just pure, crystal clear strategy.
Okay, Section 3, Ratio Constraints. Finding the impossible sum.
Consider this classic type of question. Given a base ratio of 2 to 3 to 5 to 6, which total sum is absolutely impossible out of the options 240, 192, or 160? The crucial point here, our apodictic knowledge for this problem, is that if you add those basic ratio numbers together, so 2 plus 3 plus 5 plus 6, you get exactly 16 basic parts. That means any valid total population, regardless of what the multiplier is, fundamentally relies on this building block of 16. Let's test some integer multipliers to see this in action. If we use a multiplier of 15, we get values of 30, 45, 75, and 90, which adds up perfectly to our first option, a total of 240. If we use 10, we get 20, 30, 50, and 60, summing right up to 160. Because we can only use whole numbers, these integers discussed in our source material, 192 is immediately exposed as our impossible outlier. By mapping it out this way, we avoid blindly guessing and let the underlying structure of the ratio do all the heavy lifting for us.
Let's keep this momentum going into Section 4, Strategic Percentages and Company Employee Growth.
Here's the setup of this problem directly from the source. If a company had 15% more employees in December, which happens to be 460 total, than it had in January, how many did it have in January? Now, a very common trap here is to either start randomly testing the multiple choice options or getting super bogged down trying to calculate what 15% of an unknown number looks like using fractions, like 15 over 100. Honestly, it's just too slow. We need a faster mental engine for this.
So look at this single decimal, 1.15. The source strongly encourages completely shifting how we write out percentages.
Realizing that January's population, plus a 15% increase, is simply 1.15 times January, or 1.15J, is basically the ultimate engine for percentage problems. It takes a clunky two-step thought process and condenses it into one clean, elegant equation, 1.15J equals 460. That right there is our apodictic knowledge, the clear, unquestionable foundation we talked about earlier. But, setting up the equation is really only half the battle, right? We still have to solve it, and usually without a calculator. Let's contrast the tedious long division method on the left with the strategic route on the right. Traditionally, you might try to do 460 divided by 1.15, maybe moving the decimals to get 46,000 divided by 115, and then slogging through all that long division. Ouch. But the strategic route, it looks at significant numbers. If we recognize that 115 times 4 is exactly 460, we instantly know our answer is going to be 400. We bypass the long division entirely just by recognizing those underlying numerical relationships.
Actually, there's another really cool layer of strategy here too. The source smartly points out that part of being strategic is reading the situation of the test itself. We can look for contextual clues. For example, if the word approximate is totally absent from the prompt, you can confidently expect an exact, clean answer. This means you can just rule out decimals and odd numbers entirely from the multiple choice options right off the bat. You know that 115 absolutely must divide evenly into 460. Using the test's own rules to your advantage like this is a massive time saver.
Bringing it all together, let's look at Section 5, Key Strategies and Mistakes to Avoid.
All right, let's dive into this final recap. These bullet points, these are your new golden rules. First and foremost, seek clarity before applying speed, always. Second, look for system-wide shortcuts, like adding all the equations together rather than taking the grueling long route of substitution. Third, absolutely master that 1-point-x decimal format for percentage growth. It just makes setting up equations infinitely cleaner. And finally, focus on significant numbers over doing long division. These are the specific mental engines that are going to get you to the correct answer way faster and honestly, with so much less stress.
So as we wrap up this explainer, I want to leave you with this question to chew on. What other mental engines are sitting idle in your mind right now, just waiting for the clarity to finally turn them on? The strategies we explored today, they aren't just little math tricks. They represent a completely different way of viewing mathematical relationships. As you continue your practice, I really want to challenge you. Don't just settle for the long route. Look for those shortcuts, seek the clarity, and let your mind run at its absolute full potential. Thanks so much for joining me for this explainer, and happy studying.